The last thing that I want to take a look at in this lecture are a couple of numbers that we'll be using quite often when we're looking at combustion reactions. And the first one is the air to fuel ratio, or air fuel number, and another one is the equivalence ratio. And these sometimes give us an idea in terms of, are we at theoretical air, so stoichiometric mixture, or are we below theoretical or above? And so that's the reason why we use these numbers. So the air to fuel number is basically the mass of air being combusted divided by the mass of fuel. So that's pretty straightforward. Now for methane, we looked at a oxidation reaction for methane just a moment ago. So let me pull that equation back in so we can look at the final reaction equation that we had. We said CH4 after going through and doing the balance for stoichiometry, this is what we ended up with. So that was the relationship that we had. Now, if we're looking at the air to fuel ratio, what we would do is we would take the number of moles multiplied by the molar mass of air, because remember, number of moles is going to be in kilomoles, molar mass is kilograms per kilomole, and we divide that by our fuel. And here we're dealing with methane, so we would have the number of moles multiplied by the molar mass of carbon plus the number of moles multiplied by the molar mass for, and in this case what I'll do is I'll use diatomic hydrogen. And looking at our reaction now, for the number of moles of air, that consists of both oxygen and nitrogen. And so what we have is in our balance equation 2, and then 4.76 kilomoles of air, multiplied by the molar mass for air, which we said was 28.84 kilograms per kilomole. And we want to now divide that by our balance for, first of all, we start with carbon. So in our stoichiometric balance, we have 1 out in front of the CH4. And then we're dealing with 1 kilomole of carbon multiplied by the molar mass of carbon, which is 12 kilograms per kilomole. Plus, now we're going to do diatomic hydrogen. So what we have in front of the reaction equation for the CH4 methane, there's a 1, and what I'm referring to is this point right here. There's a 1 there. And we have 2 kilomoles because we have H4, so we have 2 kilomoles of diatomic hydrogen, and the molar mass of diatomic hydrogen is 2 kilograms per kilomole. And when you go through this, you get an air to fuel ratio of 17.16, and that would be the air to fuel ratio for methane for a stoichiometric reaction. So that's the air to fuel ratio, and you can compute that for whatever fuel you might be combusting. And the last thing that I want to take a look at here is another useful number, and it's called the equivalence ratio. And the equivalence ratio is capital Phi. And for this, we take the air to fuel ratio for a stoichiometric balance divided by the actual air to fuel ratio. Or it could also be defined as the fuel to air ratio for the actual reaction divided by the fuel to air ratio for stoichiometric as well. And so if we're dealing with a reaction that is what we would call fuel rich, where we have more fuel than the stoichiometric balance, in that case our equivalence ratio would be greater than 1. And if you're dealing with a reaction that is called fuel lean, or a fuel lean mixture, in that case, your equivalence ratio will be less than 1. So those are a couple of numbers, the air-to-fuel ratio and the equivalence ratio, and they're sometimes used in order to figure out where you are with respect to the stoichiometric theoretical error value for your combustion reaction. And they do have big implications in terms of the amount of either unburned hydrocarbons or nitrous oxide formations that come out. If you have fuel rich, you'll have a lot of unburned hydrocarbons, and if you are fuel lean or you have excess oxygen, for example, in an internal combustion engine, then you'll have excess NOx formation, which leads to the photochemical smog that we talked about in an earlier segment of this lecture. So with that, that concludes the introduction to combustion. What we'll do is we'll continue moving in to looking at how we can apply thermodynamics to the analysis of reactions, combustion, and oxidation reactions of hydrocarbon fuels.